This module is covering or introducing general surface integration. In previous modules, we've talked about surface area integration as our lead-in to surface integration more generally. That's what we always do with integration, talk about some sort of area, volume, or arc length first. So now we're going to talk about general surface. Now, so what does this mean? The concept is that we have in space, say in this room, we have some function, a scalar function for now, like temperature or power, that is a function of position in the room. So every place in this room has a different temperature, let's say. Okay? And then, so that function that describes temperature is we're going to call G for now. Now, what we want to integrate is not just that total temperature, is I want to take a sheet, some surface that I'm going to lay out in this room. Could be the surface of a table, could be a blanket hanging in space, could be some foil shield that we have that we care about. And it's sitting in this room so that each location on that surface is experiencing some different local temperature, because we have the temperature field, and we're placing a surface inside that temperature field. And I'm going to integrate that temperature field over the surface. So for example, if it was temperature in the room, and say you wanted to do something like, I want to try to calculate the total power absorbed in my sheet, because I care about the sheet because it's a heat sink or a shield or something like that. I want to calculate the total power absorbed in this sheet at any instant in time. And I'm going to assume that the local power absorbed is proportional to the local temperature in the room. Okay? So I could build an integral where I roam over the surface of the sheet, summing up the temperature as I move over that surface. And that's what I want to do. So it's a real thing to do in actual applications. You might soon go, well, what happens if it wasn't a scalar field in the room? What if it was like the electric field and it was a vector field? Soon enough. We'll get to that soon enough. When we integrate a vector field over a surface, we have to start thinking about components, and it becomes what we call a flux integration. And that's what's going to happen after we talk about this general surface integration. Okay? So the basic form is I have a integral over a surface, which is integrated by the double integral sign. S, when we use an S, usually that means it indicates a surface. You have to know from the context of a problem what we're talking about, but here that's what we're doing. The ds also indicates that you're integrating over surface elements. Okay. Now, this is the picture, right? We have our xy space, we have G defined everywhere in the universe in principle, then we have a local surface S, which could be small, could be very large, and I'm going to integrate G as it varies over that S. Okay, we get it. Now, to proceed, the thing that starts to be complicated about surface integration is you start to have options that you didn't have when we were doing simpler double integration. It was more obvious what you did. Now you generally have a series of cases that you could use to execute this integration. Okay? And so they're kind of captured here. They're kind of obvious. And right now when we just think of Cartesian coordinates, that's how we're going to introduce this. You basically, what we want to do is convert the surface integration to a double integration over a region under the surface. Now under is a bit semantic, but when we think of it in this case here, which is also kind of how I sort of almost drew it over here. It's the natural one for us because we're used to thinking of z as a height over x and y. If you think of your surface as that, as some height function z over x and y, then what we want to do is you think of, we have our surface and then we have a shadow that casts down on the xy plane, and that's where we're going to roam our integration over. Our limits of integration are going to be based on A, and we're going to integrate something related to the height of the surface above there and the value of G as we roam over that surface. So we convert the surface integral into an xy integral over the region A. You don't have to do that though. We obviously could take the same surface, and instead of casting a shadow down on the xy plane, you could cast a shadow over to the xz plane. Okay, like here. So you cast it this way. Same surface, projects a different area in the xz plane, and we could instead calculate over the xz and think of some height function and gx yz over this. Or, the last one's probably obvious now, you could project into the board and cast a shadow down or into the yz plane. Okay. Which you choose to do, so first of all, it can't matter which one you use. You have to get the same answer no matter what you do. Okay, so that's comforting. But what's not comforting is that usually one of the three is much easier than the others. And that's the one we would choose to use. And it's one of these cases where we have to practice a bit and you get a little experience in sort of identifying, well, which one would I want to use here, right? You know, again, at sort of a norm and a thing we're used to, not to have too many new things at once. We're going to look at our first example that is kind of like this. We're casting a shadow down on the XY plane. We're used to thinking that way, but we will look at other cases. Now, before we get into a specific example, let's just look at the general form of this. And it draws, it's the same form as we had when we did surface area, except now we have this G function in not addition, as a product in the integrand. So there are three forms that we kind of remember when we're doing this, okay? So, and you'll see the pattern in them. Once I describe one, you can sort of figure out what the other two look like, but I'll write them all down here just quickly. But in case number one, where we think of, we're basically, I'll say it in this, we remove Z and integrate over XY. Plane region. This is the kind of natural one for us. We think of the sheet lying up in Z over top of X and Y. We project downwards, we eliminate Z, and we have a double integration X and Y. When we do that, this integral, in case number one, this integral, okay, ds would become this integral R, and this R is that region in the XY plane underneath here. If this had some region here, this would be R. Yep. So we have our function. Now look at this. We have X and Y, but now if we have any Z's in this integrand, we replace them with the function XY, okay, which is the height function for the surface. Okay. So, and then we do the same surface area to integration region conversion as we had in surface area, where we actually looked at this element. So we look at partial of the height function with respect to x squared plus the partial of the height function. We sum those, and then we have dA. Okay. Now in this case, this here will be dx dy. And these limits will be limits in x and limits in y. G, x, y, z is some function that we're given. Again, it defines the temperature in the room. Okay. The surface that we want to integrate over is what defines f. So f, x of y, is us describing that surface as a height z over the xy plane. That defines the surface. So gx and y is not the surface, or gx, y, z is not the surface, but we're replacing z with the surface definition and then integrating over xy. Okay. If instead, we remove, whatever is the second one here, remove y and integrate over the xz plane. Okay. So this is like projecting left to right in the traditional system. Right? Then we'd have, and you can sort of, once I write this one, the third one will be obvious. So now we have our temperature distribution, say. It's a function of x, but now instead of y, we're going to have some function that describes the surface y height as a function of x and z. Okay, so this is that comes from the surface. The reason I'm writing little g here, whereas I wrote little f here, is they're different, right? In this general function g, x, y, z, that's the temperature of the room. But the surface is, if I think of the surface as a height over x, y, that's one function. If it's a height xz, like a height over the xz plane, that's a different function. Okay? And then we take this and we go 1 plus, and now we go partial g, partial x, whatever's left, right? Partial g, partial z squared. That converts that surface area element to our 2D or double integration element, and this guy here will now be dx dz. And these limits will be limits in x and limits in z. Finally, the last option we have, remove x and integrate over the yz plane. Okay, so this is sort of case, this is the second sort of situation, this is the third. Okay. Then this surface integral, s, now we'll write, we'll have h, so I can eliminate x now with some function of y and z, y and z, that's the temperature distribution. And I'm just saying temperature as our concrete example. This is, who knows what G is, depends on what we're doing. Okay, square root 1 plus, now you get partial h, partial y squared, plus partial h, partial z squared. dA, this guy will be dy dz. These will be limits of y, limits of z. There'll be no x left in here once we make that removal. Okay. Okay, so those are the options. That's how we set up a surface integration solution. Okay, we'll be given some description of this. We will decide and visualize this surface, as well as understand the form of the function that we're integrating over the surface. And then we make a decision. We decide whether it's easiest to think of this surface in general as a surface over x and y, or a surface over x and z, or a surface over y and z. And depending on which one we choose, we convert the surface integration into a double integration, one of these forms, eliminating, if it's eliminating z, or eliminating y, or eliminating x. Okay? And when we do a first example, we'll do a pretty simple one right now. It becomes pretty obvious what you're doing. Okay. And just for color, right? I give on this equation sheet, if you feel like, I don't feel like I can remember this, on the equation sheet on the exams, I don't give you all three forms because they're kind of redundant. You kind of get one, but I give you one of these so that you can sort of remember, oh yeah, if I'm eliminating this, it takes this form, and then from this one, you could remember the other ones if you had to. So you have that on the equation sheet already, just in case you were forgetting. So let's look at a reasonably simple but non-trivial example, right? And again, we're not doing surface area integration, we're integrating something over a surface. Okay. So this actually is, what is this? This is section 913, problem 16 from the textbook. Okay. It says evaluate this surface integral. Okay, yeah. Probably need to say that. Just say evaluate the surface integral for G equal. There's some goofy made up function, right? We make these up so that the actual integration that we end up doing isn't too difficult, because we're not trying to squeeze our ability to actually execute individual integrations. We're trying to learn how to set these things up. So we try to make these things not crazy. Okay, so that's the function, like the temperature in the room is defined everywhere in the universe, say. And then we have surface. There should be two functional definitions in these problems. One functional definition is the thing we're integrating. The other functional definition is what surface. Sometimes the surface is given as a function. Sometimes it's described as the intersection of a whole bunch of curves. Depends on the problem. Here we have a bit of that. So S is the portion of Z equals 2 minus x squared in the first octant, right? Bounded by x equals 0, y equals 0, y equals 4, z equals 0. Okay, so this seems kind of crazy, but it's not that difficult once we draw it out. I'll draw that, then I'll erase this part, and we'll go and execute it. The execution isn't really that long. Okay? But like all these, what you have to do is sketch it. You have to visualize it, especially in these ones where it's surface integration, where you have this choice. Because without visualizing, it's very kind of difficult to make a educated, like a judgment on which way will be easiest. Okay? So let's just draw this thing. Okay. So I've got, here's it. I'm gonna extend this a bit because of the nature of this particular question. Okay, and this is y. So what does this look like? We're not drawing this, right? We're drawing this. So it's the first thing. The portion is, well, say first octant. Okay, first octant means x greater than 0, y greater than 0, z. So we're just in this octant. We're not into the board. We're not to the left. We're not down. Okay, that's the first thing. Then z equals 2 minus x squared. Well, first thing, it doesn't depend on y. So whatever we got here is constant with respect to y. Now, it's quadratic, so it's not a plane. It's something else. It's curved. At x equals 0, z equals 2. So right here, definitely it goes through that point there, 2. Okay? And it doesn't matter what y is, so that's a line that will define this thing. Okay. And then, how does it vary with x? Well, z equals minus x squared. Okay, so z equals minus x squared is a parabola that's negative. Okay, so if you were just drawing a picture of z versus x squared, it would look like a curve down. So here, what z minus x squared would look like, z equals minus x squared, would be a parabola starting here and going into the board, right? But we're adding 2 to it, so we're shifting it out. So this is really sorry, I'm saying that in the wrong dimension here. This should come down, okay, like this. Okay. It would continue. So this curve here, right, is z equals 2 minus x squared. Okay, so it kind of looks like half a dome, right? It's just a curve down from z equals 2 down here. Okay, it's got a plane at x equals 0, a plane at y equals 0. Okay, we're limited here at y equals 4. That's from this guy here. Okay, so it's just this. It's just this surface. This surface here. Okay, what's this value here? Where we cross there? Well, that's at z equals 0, so that's a square root of 2, right? Because at z equals 0, x squared equals 2, so that's the square root of 2. That's the, up here, right? That's our surface. Okay, looks like half a shed or something sitting, right? Domed up. Okay, so we have to decide, are we going to think of this as a surface above the xy plane? Is this a surface above the yz plane or a surface above the zy plane? So one thing you can't do is we can't think of it as a surface above the xz plane because it reduces to a curve there. We lose the surface definition. So we have to think of this as either a height or an into and out of the board one. We're going to think of this as a height over the x and y plane. It's sort of set up for that. Okay. So we're going to consider this region down here, right? The region A that we're actually going to integrate over. And it's going to have limits, so it's in the xy plane. It's going to have limits from x equals 0 to root 2 and y equals 0 to 4. Okay, so it's a rectangular region in the xy plane, which is going to make this relatively easy to do. Okay, so we've got our z equals f of xy, right, which is 2 minus x squared. That's our height function. So we're going to need the partial of that function with respect to x, right, which is minus 2x, and the partial of this function with respect to y, which is 0. There's no y dependence. Okay. So our surface element will look like square root of 1 plus the partial with respect of the surface with respect to x squared, so that becomes 4x squared, plus the partial of f with respect to y squared, which is 0. And we have dx dy. Okay. Now, so let's go over here and just build the integral. So this thing, S, G, ds, that's our surface integral. This thing is going to be, okay, we'll just leave this as, I'd like to call it, in my notes, no, sure, I'll call it A. I called it A here, so we're integrating over the region A. Okay. So, first thing, I erased it, but what was G? G was, okay, this whole thing is G. That was given to us in the problem. I didn't derive this, I didn't substitute this. This came from the problem. Okay. And then we have our ds part, so I have 1 plus 4x squared dx dy. Now, what's the thing I haven't done? Okay, something's wrong here, because I've got a z here. What I'm supposed to do, so this is g, what I need to do is move g to a function of x, y, and then f of x, y. So I eliminate z in favor of this function. So this thing should be a x, y, 9 minus 4, and what's z? On the curve, z is 2 minus x squared. Okay, then I have 1 plus 4x squared dx dy. Okay, good. When we cast our eye over this, this better be x's and y's. Okay. So, we will simplify this. The other thing we can do as well is set our limits of integration. The limits of integration, it's a rectangular region, so the limits on x are independent of the limits on y. So this thing is going to turn into, if I think of y outside, okay, so 0 to 4, so it's, when in doubt, if you've got 2 and you want to be clear of which limits you're writing, just put like a, so I'm saying y equals 0 to 4, that's cool. And then x equals 0 to square root 2. You don't have to do that, but that's more clear. Okay, and I've got x, and I've got y. Let's just simplify this. This is 9 minus 8 plus x squared, so this is, this should be, minus 4x squared. Okay, so that's plus 4x squared. So this becomes 1 plus 4x squared. Yeah? Good. At this point, we're doing double integration from 3 weeks ago. Okay? There's nothing else to this. We've used our definition of the problem, we've identified the surface, we drew it out, and defined the limits of integration. We decided we were going to do this as a surface over the xy plane, so eliminate z in our overall function, and now we've reduced it down to this. So that's cool. I'm going to leave the picture up just because it's nice to do sometimes, but we don't really need it. Now we can just go. So 2 things we can do here is the we'll simplify. Okay, so let's just go up here for a sec. Okay, so this thing equals. Now we don't always do this, but we've done double integration for long enough now. I think you can handle this, right? So this y, there's nothing in here that depends on y, and these limits don't depend on y. So I can think of this as a product of 2 integrals. So I've got 0 to 4 y dy times 0 to square root 2. And then I've got, x times, and I've got 1 plus, okay, so this is 1 plus 4x squared to the 3 over 2. Right, because I've got there and 1/2, okay, dx. Okay, you can see the substitution going to happen. You can see the solution here going to happen, right? So this thing becomes, okay, so this is going to be y squared, oh, let's not do it in our heads. Y squared by 2, 4, 0, okay? And then just leave this for a second. 2, x, actually I'm just going to, it seems like this is not important and it's not really, but okay, so that thing becomes 16, 8 minus this is 8. 8, okay. And then we're going to make our substitution. U equals 1 plus 4x squared. So du equals 8x dx. So x dx equals 1 over 8 du. Do you have to be really slow like this every time? Well, I do, so you probably do too. But it's a choice. Okay, so I'm just going to say here, okay, so I've got u, so I'm going to leave x equals 0 to root 2. I've got u to the 3 over 2, and I've got x dx, I've got 1 over 8 du. Okay, let's just go slow. Okay, so our integral, you don't have to keep writing this, but we do. Okay, so I've got 8, and we got 1 over 8. Okay, I got 1 over 8, gonna kill that. Okay, so those die. And then I've got, let's see here, u to the 3 over 2, so that becomes u to the 5 over 2 divided by 5 over 2, right? Yeah. X equals 0 to root 2. This becomes 2 over 5. And then we can put our u back in, 1 plus 4x squared. And now do the real calculation here. So, okay, 2 over 5, and I've got 1 plus 4, 2, 2, so 8 minus 1. Wait, okay, what's that? 5 over 2, almost forgot that. So this, just be a little careful. This here, 1 plus 8 to the 5 over 2 minus 1 plus 0 to the 5 over 2. Okay. It's easy, I do this a fair bit, it's easy to drop that as we're ripping through here. So this is 9, so this is 2 over 5, and we got 9 to the 5 over 2 minus 1. So that's 2 over 5. 9 is 3 squared, so this is 3 to the 5th minus 1. You could leave it like that. This, I happen to have done this one, so this becomes actually 2 over 5 times what? 242. Okay, so 484 over 5. You can leave this. Here is all where you need to go, right? These become a little bit of a calculator thing once we've done them. Okay. Now, so that's our first example of a true surface integration beyond a surface area integration. We had a relatively simple surface. We had the choice of thinking of it as a height over x and y or a height over y and z. If I would have made it a height over y and z, I would have had to solve this for x and say that, I would have said that x squared equals z minus 2, so x equals square root z minus 2, right? That would have been the height x above z, above the xy plane, right? And I would have put that in. Now, right away, that becomes not attractive. As soon as we know from doing these integrals that the more square roots and stuff you build into this, the crappier they get. And it's nice if you don't have that. Now, we did have square roots anyways, but this is maybe one of the reasons why we thought of this as a height over the xy plane, because we were given z straight up as a straight polynomial height over the x and y plane. Didn't depend on y. That seemed kind of attractive. The region is rectangular in the xy plane. It's also rectangular in the yz plane. It would have been pretty similar in difficulty, right? But that was the choice we had. So then we substituted, got rid of z in our integrand, right, the g function, and we had a function of just x and y. Because it was rectangular region, the actual integrals separate, and because the integrand was such it was just a factor in y, that became a product. So we pulled it into a product of two integrals. That's not always the case. It's not even often the case. It's sometimes the case. You gotta be a little careful when you do that. Easy to make that mistake. But if you can, it's nice to do. You eliminate the y part. Then, substitutions and stuff, we went through and worked this part out. This is from first year. So, it's easy to make a little mistake in there, but it's fine. When it comes to interpreting the result, so when we were doing surface area, the first thing, we better have a positive answer. Okay, so now that's not the case, right? Because if, let's say g of x, y, z was negative everywhere, there's a big negative number, then you're going to get a negative answer for your summing that integral over the surface. So we can't make the same easy judgments of whether the solution makes sense or not, like we could with surface area. Okay. Now, our g of x, y was, what was it? It was, we had g equal x, y, what do I have? 9 minus 4z. So, for z, everywhere in this situation, z is less than 2. So z less than 2 means everywhere here, and we're in the first octant, this actually is positive for all the variables in our problem. So actually, we know this is actually greater than 0 for all x, y, z on our surface. So we do expect the final answer to be positive, and it is. Good. So that's something you could do. It's hard to do a lot more, right? It's hard to do a lot more on this. I guess one thing you could do too is you say, like, I don't know, how big an answer do we expect to get? This is something on order z, this is x, y's. X's and y's are varying to be larger than 1, right? We're not integrating within a region that's 1/2 by 1/2 by 1/2. We're integrating within a region that's like 2 by 4 by stuff. So we're summing up a bunch of products of numbers. It makes sense that this thing, I don't expect this thing to be 10 to the 9. But I also don't think, I wouldn't expect this thing to be 1 divided by 92. Right? It makes sense that it's order 10. Just given these values, x, y, 2, 4, 10, it sort of makes sense that it'd be that kind of big. One other thing, there's no way it would come up here, but we don't expect to see pi's in here because we aren't doing anything in polar coordinates or anything, so that wouldn't happen anyways. It's more the opposite. When you're doing polars, if you lose the pi, that's concerning sometimes. Okay, so that's a relatively straightforward first example of a general surface integration. We'll probably do one more of these or a little bit, but very quickly now we're going to move on to the next thing, which is, well, what if we're integrating a vector field over a surface? That's interesting, and we have to think about flux. Okay, so that's going to come up next.